So the second in-class exercises ask you to simulate a single queue, but the underlying data structure is not a queue. What you have instead are two stacks. So how do we simulate the functionality of queue using two stacks? Okay, so this is the almost like a template, the pseudocode for the DQ operation. You can treat that as a given, right? You want to design your DQ this way. So if you're going to DQ, right, by using two stacks, we use stack 1 to represent the first stack, and you can imagine that we should also have a stack 2, right? So if the stack 1 is empty, you will return an error. If stack 1 is not empty, you will directly just pop the content. This is a very important information because it basically hints that the order in which you can pop the information from the stack will be consistent to that of the queue, right? Which basically boils down to this, right? So if you draw it out, you have stack 1, you have stack 2, right? And you have an imaginary queue on the right-hand side. This is your head, right? So inside this queue, right? Let's say for user imagine that you actually have the element of 1, 2, 3. And when you DQ the element, right, the expectation is that the element should come out in sequence, 1 after 2 after 3, right? And we say that based on the problem statement, the sequence inside the stack 1 should be consistent to that of the queue, right? Because if we need to DQ an element from the queue, it's the same as just popping from the stack. But the data acquisition order of the stack and queue are opposite, right? Because for the queue, it's first in, first out. But for the stack, it's last in, first out. So if you want to maintain the sequence, basically it means that inside the stack 1, the data must be arranged this way, right? Smallest value, the most recent value reflect the head of the queue, right? So you have 1, 2, 3, 1, 2, 3. So if you continuously just pop the value of stack 1, right, you should actually get exactly the same order. All right, so this is based on the assumption that when we DQ, right, we'll simply return the pop value from the S1. Right, so this is the requirement, right? So now the challenge here is that how do we write the in-queue operation based on this information? Because you see that if in-queue happens, let's say a new 4 come in, right? It should be after 3, but we cannot put 4 over here, right? Because if you put 4 over here, we have to follow the first in, first out principle. Sorry, the last in, first out principle, which means that the next DQ, you're going to remove 4, not 1, right? So we have to do something to fix this, right? It means that we have to take advantage of S1. All right, so key idea over here is that when new information come in this example 4, right? We have to make sure that 4 somehow can be almost inserted at the bottom of stack 1. But for stack, there's no insertion, right? So this is where the second stack will come in, right? So we are going to use the second stack as a buffer, right? We can dump everything from stack 1 to stack 2, right? So if you do that, the new arrangement of the item will become like 1 to the bottom, 2, and then 3. And stack 1 will become empty, right? So now when the new information come in, you can put the new information for over here. This order will be correct. But again, because we operate our DQ happen at S1, we have to again dump everything from S2 back to S1. If you do that, you will get the correct sequence again, right? 4 is being popped and then pushed to the bottom of S1, followed by 3, 2, and 1. And S2 now become empty again, right? So now we are prepared. We are prepared for the next pop operation. Sorry, DQ operation, right? If we need to DQ, we'll get that from S1. And this sequence is still correct. We still have the correct sequence of 1, 2, 3, 4. All right, so this is visually how the algorithm should look like. So we can turn this visualization into the actual pseudocode, right? Okay, so we follow this sequence, right? The step number one, when we are enqueuing a new information, right? We want to enqueue, let's say a new data, we call it D, right? This is the data that we like to insert. All right, so the first step that we do is that we should actually move everything from S1 to S2, which basically means that we can use a while loop while the content of S1, the count of S1 is greater than 0. What we do is that we're going to push the element into S2 from S1, right? Two coming into one. And of course, if you wish, you can actually break it down into two steps. You pop the element out, store it somewhere, and then just push that new element into S2. That's also fine, right? But over here, what we do is that we just pop the element from S1 and immediately we push it to S2, right? So this corresponds to the step number one over here, right? And then we will push the element, right? We'll push the element, new element into the stack 2. We push D in, right? So this reflects this step over here, right? This is step 2. Finally, we restore the content of stack 1, right? We repeat the same process, very similar to before, but this time what we do is that we look at S2. Well, S2's content is greater than 0. We are going to push the content from S2 into S1. But we pop from S2, but then we write it back into S1, right? So this corresponds to step 3, right? So we have this step 1, and then this is the step 2, and then this is the step 3, right? So then we completed the implementation of enqueue as well, right? So dequeue is designed this way, which means that for the pick operation, it's also going to be the same, right? So if we look up over here, this is what we have. Dequeue is simply returning the element that we pop from S1, right? Which means that if we want to do a pick, right, we can do the same, right? We just return our pick from S1, right? Because everything in S1, we assume that it follows the order that is supposed to be in the queue, right? The only complication come in queue, right, over here. Okay, so in terms of complexity, our assumption in the problem statement says that the push and pop can both assume to be a constant time operation, right? So you can have O1 over here as a result, O1 here as well, right? The complexity here then need to be counted, right? Because here, for every element inside S1, we push it to S2. So here you can see that we have one pop operation, one push operation, and in total we have n element. So it's going to be 2 times n, right? Suppose the existing element is n. And then we push one element, this is 1, right? And over here, again, now we have a n plus 1 element. We pop from S2, we push it into S1, again, 2 operations. So 2n plus 1 plus 2n plus 2, right? So roughly speaking, if you want the exact count, it's going to be 4n plus 3. But this is just On,